In this lesson, we will be looking at permutations, combinations, and the binomial theorem. In this lesson, we will begin looking at combinations.
So like it says right here, a combination is a grouping of a set of elements in which the order of the elements is, and here's the big one, not important. Okay, that's what differentiates a combination from a permutation. Now, here's some of the notation. Okay, when we do a combination here, it's n r, and you can see in this little array here. This is fairly common, although what you're going to see here, we'll zoom in a little bit here. What you're going to see most of the time in our applications here will be this notation, NCR. And on the calculator, this is the one that they're going to use as well. And the formula for a combination is n factorial over n minus r factorial. Now, if you take a good look at that, you'll notice if I cover up the r factorial in the denominator, this is a permutation, NPR. Okay, there's your n factorial, your n minus r factorial. So really what's going on here, a combination, NCR, is going to equal NPR divided by r factorial. Now let's just talk about what this notation is saying here. So NPR is just the number of ways you can permute a group of r objects from a set of n objects. And then what we do is we divide by r factorial. Well, what is r factorial? Well, all by itself, just think about it like this. If you cover that up, you just look at r factorial. R factorial is the number of ways of permuting r objects. So what you're doing here, what a combination does is you're reaching into a group of n objects, you're grabbing a set of them, okay, r of them, and then the permutation is organizing those, and then what the combination does is simply divides out the different ways you could organize that. So really what you're left with is just the selection. Okay? So a combination is really just a way of selecting the objects if as long as order doesn't matter. Okay? So if you take a quick look at this, now I'll zoom out here a little bit. So this is a really good way of thinking about it here. There are 6 permutations of the letters in the word cat, C-A-T. Okay? You got C-A-T, C-T-A, T-C-A, T-A-C, A-T-C, A-C-T. All those are distinct permutations of those letters here. However, there's only one combination of those letters. Just CAT. When order doesn't matter, as long as you're just grabbing those letters together, that's it. There's only one way to choose to have those letters. Doesn't matter what order, right? If that doesn't make a lot of sense right now, just watch as we go through some of these next examples here. It should start to come together. The key thing that you want to recognize here is that what we've got here is a selection. Permutation is about arrangements. Combinations are about selection. Okay, just getting the objects out of that set. And you want to remember the notation here, specifically the permutation, the factorial notation, the factorial form of the combination. And this can be quite useful, this NCR is equal to NPR over r factorial. All of that's really quite useful. Now let's take a look at some examples.
5 students are being selected to form a committee from 8 females and 9 males. How many committees are possible if the committee must have any 5 people?
Okay, so in this case here, if we only care about grabbing a 5 people or 5-person committee here, this is really quite a simple question to work with. Now you just got to figure out how many people do you have to start off with. Well, we had 8 females and 9 males, so it's 17 people. We don't really care what order they're chosen in. Okay, what matters is belonging to the committee. So order is not important here. So this becomes 17 choose 5. Now let's go to the calculator and have a look at how you do that. So we're going to enter 17, then we're going to press our math button like we did before with permutations. We're going to go over to the probability menu, and then you can see number 3 is NCR. So there's 17C, and we're interested in 5. Okay, so 17 people to choose from, and we're going to choose 5 of them. And so there are 6,188 ways this could happen. There you go. Remember, order is not important here in this kind of a problem.
exactly 3 females and 2 males.
Now, in this question right here, we want to be careful that we read it carefully. We want to choose a committee that has exactly 3 females and 2 males. Okay, now think back over the work that we've done up to this point here. And means multiplication. So exactly 3 females and 2 males, we're going to be multiplying 2 combinations here. Now, to get our 3 females, exactly 3 females, we're going to take a look at the fact that how many we have to start off with. And we had 8. So that'll be 8 choose 3. Okay, and we're going to multiply this by our choice of males there. And out of, we've got 9 males to choose from, and we're going to choose 2. Okay, now, in most of the applications that we do with combinations, particularly when you're multiplying them together, what should happen is that the first numbers in our combination notation should add up to the total number of people that you're choosing from. Okay? So these two numbers, add them together, 17. That's the total number of people that we're choosing from. The 3 and the 2, the secondary numbers here, okay, really what our R values are in both cases, that should add up to the size of the group we're choosing. Now, there are some exceptions to that rule, but if you follow that rule, for the most part, you should be able to avoid some pretty serious pitfalls. And I'll try to point your attention to 1 or 2 of these issues as they come up here. But let's enter this into the calculator. So make sure we put brackets around these things so that we're not bumping into having them bump into each other. We don't want to inadvertently put numbers where they don't belong here. So 8 choose 3. We're going to multiply this by 9. And we're going to choose 2. So there's our 17 people we're choosing from, the 5 people we're choosing. And it turns out we got 2016 different ways that can happen.
Jill, one of the females, and exactly 1 male.
Okay, now this is an interesting question because it basically draws your attention to an idea that can be misunderstood, or a question that can be misread very, very easily. Okay, so here's one of the stipulations here. First of all, Jill, okay, one of the females, she has to be on the committee. Now, Jill is one of the females here, but we're not going to choose her by writing down 8 choose 1. That's incorrect. This 8 choose 1 would mean from the group of females we're going to choose one of them. But that's not what we're doing. We're choosing a very specific one. We're not choosing. You don't want to think of this as I'm choosing. Like, this isn't a probability question. I'm not asking what's the probability that I get Jill. No. I am choosing Jill. Well, how many Jills are in the group? Well, there's only 1. So there's 1 Jill, and I'm going to choose that 1 Jill. Now, once we've chosen her, okay, we're told here that there's exactly 1 male. Now, we're not told who that male is. It's just 1 male. So of the 9 males that we can choose from, we're just going to choose 1, exactly 1. Now, see, here's the difference between these two. This is choosing a very specific person. This is choosing anyone, not a specific male, just a male out of the group here. Now, to finish this problem, though, now look at this. This is telling us right now that I'm choosing from 10 people, and I've only chosen 2. Now, that means there's another group here that I have to choose from, and that's the rest of the females here. Okay, there were 8. Now there are 7 left to choose from. And to finish this one off here, I've already got 2 people chosen. I need to choose 3 more females to finish off this group the way it's described. Okay, so now let's go to our calculator here. And I'll do 1, choose 1. Now I'm doing this right now, but how many ways can I choose 1 object from 1 object? Well, just 1. Okay, so that's only going to be 1, so that's not such a big deal. Now I'm going to do 9 choose 1, write that down there. And how many ways can I choose 1 object from a group of 9? Well, just think about it for a second here, and it should be clear to you. Well, that's 9. So this is actually going to be 1, this is going to be 9. It's this last one here that I'm not entirely sure of. So, whoops, sorry. And, 7 choose, and what did we need? We needed 3 to finish this off. And so there are 315 different ways we can choose a committee that has Jill on it and exactly 1 male.
1 female or 2 females.
Okay, now notice the important word in this question, and that word is or. And remember, what the same meaning that this thing had in the past, it has right now. That word or is going to mean addition. So we're going to add 2 different scenarios here that can't be done simultaneously here. So first of all, 1 female. I'm not specifying who that female is, so that means of the 8 females that we've got, I'm going to choose 1 of them. Now, that's not enough for a committee, because I need to have females and males, especially if I've only got 1 female here. I'm going to have to have 4 males to finish this thing off here, because we need to have a committee of 5. So, here we go. This is going to be 9, choose 4. So 17 people, and we're choosing 5. Or this could be 8, choose 2. Okay, in which case, once I've chosen the 2 females, I now have to choose the 3 males. So it's 2 women and multiplication, 3 males. So now, once that's written out there, we can go to the calculator. And we've got, what was it again? It was 8, choose 1, 9, choose, what did I have here? 4, add, and now here's the other scenario here. 8, choose 2, 9, choose 3. So altogether we've got 3,360 different committees that we can create that have either 1 or 2 females on them.
How many possible selections of 6 numbers can be made from the numbers 1 to 49, as in the game Lotto 649?
Okay, now to understand how this, or to answer this question, you've got to understand a little bit of something about the way this Lotto works here. Lotto 649, you've got 49 numbers to choose from, and you're just going to choose 6 of them. So you've got this piece of paper here with these numbers on it, and you're just going to scribble in your choice of numbers here. So order isn't important. Okay, you don't gain anything, or there's no even option of, for example, if you choose the number 6 and then you chose the number 49. Order is irrelevant. Okay, you're going to shade in probably the 6 first, shade in the 49 down here, and that's it. It's like a little Scantron sheet that you're filling in here. So order's not important. This is a combination. You have got 49 numbers to choose from, and we're going to choose 6 of them. Okay. So let's take a quick look. This is actually kind of an interesting result here. 49, choose 6. And look at that result. Okay, we get 13,983,816 different ways that can occur. When you just consider, like, with just 49 numbers, okay, that's a staggering number of ways you can choose 6 of them. And remember, order isn't even important here. It's not even like if you included, for example, let's just take a quick look at it. Hey, if order was important, this would have been 49, and we'll do permutation here just to see. 49p6. So if order becomes important, look at it. The calculator has to use scientific notation for this. This is a 1 followed by, and then you move the decimal over 10 times here. Isn't that amazing? It's just unbelievable to me how quickly these numbers grow here. Anyway, so just a little under 14 million different ways you can fill in that lottery ticket.
How many 5-card hands can be dealt from a standard deck of 52 cards if there are no further restrictions?
Okay, now we're going to take a quick look at a deck of cards. Okay, and dealing out different hands here. You're not typically going to get questions like this on exams. I mean, you may, for sure, but usually on the major exam here, they won't do that because there's a significant portion of the population that won't be familiar with a deck of cards and the games that are associated with it. However, that does not deter us here because this is an excellent source of questions in this kind of a category here. So we are going to look at it for now just because there's some really interesting math here. So how many 5-card hands can be dealt from a standard deck of 52 cards? Okay, if there are no further restrictions. Okay, so no further restrictions. We don't really care what order it is, what order you pick them up in. You just want to have them in your hand here. So that's going to be 52, oops, sorry, not choose 2. 52, choose 5. Okay, so go to our calculator here, 52, choose 5. Order's not important. And here we go here. We've got, what is that, 2,598,960 different 5-card hands we can choose.
They must only contain hearts.
Now granted, to answer this question, you have to have a bit of a familiarity with a deck of cards here. They must contain only hearts. So again, just in case you're not familiar with a standard deck of cards here, we're going to have 13 hearts, 13 diamonds, 13 clubs, and then 13 spades here. Okay, and these are just different pictures that get drawn on these cards here. There's 13 cards that have these heart symbols on them. What if they must contain only hearts? Now, the way you want to think about problems like this, particularly when we're throwing a restriction on here, is you want to think about it as if you're playing cards with a friend, and maybe as if you're cheating, right? As in you're going to deal your partner a specific set of cards here, a specific hand here. So now the question that you've got here is if you're going to deal to your partner here a hand that contains only hearts, what decision do you have to make? Okay, what is the decision that you have to make here? Well, you've already decided that they're going to get hearts, so that's not the decision. You don't have to choose which suit you're going to give them. We've already chosen hearts. So now there are 13 different cards you can choose from in that set, okay, in that suit. What you have to do is choose, of those 13, you have to choose 5. Okay, so now let's go to the calculator here. 13, choose 5. And we get 1,287. So there are 1,287 ways that you can choose, or you can basically decide or pick a group of 5 cards from that set there. I hope that makes sense here. That would be the exact same, by the way, if we chose diamonds, clubs, or spades. It doesn't really matter what the suit is. There are 13 cards to choose from, and I only need to grab 5 of them. Again, order's not important when you're putting together a hand.
They must have 3 red cards and 2 black cards.
Okay, and again, just a little bit of background, just in case somebody's a little bit weak with a deck of cards here. We're going to have three red cards and 2 black cards. Now, the hearts, okay, and the diamonds are red. The clubs and the spade, oh, that's a terrible spade. Oh, boy, but you get the idea. The clubs and the spades here are both black, which means there are 26 red cards and there are 26 black cards in a deck of cards, okay? So, again, let's pretend that you're cheating, right? And you're going to deal a very specific hand to your partner here. You're going to deal 3 red cards and 2 black cards. Well, what choices do you now have to make? We already know you're going to send red cards and black cards, so you're not choosing that. What you're going to choose is which red cards are you going to send? Well, you're going to send over, and you've got 26 to choose from, and you're going to choose 3 of them. And remember, and means multiplication, 2 black cards. There are 26 to choose from, and you're going to choose 2. Okay? So now, let's go to the calculator, and we'll do this in parentheses here. So 26, choose 3. 26, choose 2. Okay, and there's our 5-card deck. Remember, we're choosing, the entire deck has 52 cards in it. There's your 26 plus 26, 52 cards. I'm choosing 5, 3 plus 2. There's my 5. Press enter. Ooh, and we get 845,000. 845,000 different hands that we can create that have 3 red and 2 black.
They have 4 jacks.
Okay, and again, a little bit of background, just in case this question doesn't make sense. They have 4 jacks. So in a deck of cards, in a suit, I should say, there's 13 hearts, 13 clubs, 13 diamonds, 13 spades. In those 13 cards, they start from 2. They're numbered from 2 up to 10. And then you've got a card that's called a jack, a queen, and a king. And finally, the ace, which kind of doubles as a 1, but we call it the ace, and so we give it some status over there. So, 4 jacks. Well, those 4 jacks would mean that they're coming from each of the different suits here. So, the jack of hearts, the jack of clubs, the jack of spades, the jack of diamonds. We've got all 4 of those. Now, again, let's put this in a context where you're cheating. So if I'm going to pass over to my partner a hand that has 4 jacks in it, what choices am I making? Well, we've already decided, okay, that I'm going to give that person 4 jacks. So that's choice has already been dealt with. That's not the choice that I'm making. The choice that I'm making is, what am I going to do for that last card, the 5th card? Okay? And in that case, what I've got to do here is 4 of the cards out of the 52 are taken up here. And you might even want to think of it like this. There was let's say the jack of hearts, I chose it. There was the jack of clubs, whoops, not 2, you can't do that. Jack of clubs, I chose it. There's the jack of diamonds, I chose it. There is the jack of, what am I at, spades, I chose it. So 1 choice, 1 choice, 1 choice, 1 choice. And now, what am I left over with? Well, of those 52 cards, I've already dealt with 4 of them. So what I've got here left over is 48 cards, and I have to choose 1 extra card out of that group of 48 to finish off my hand, my 5-card hand. This is the only one that's going to give me any kind of interesting number here. And how many ways can I choose 1 card out of 48? Well, the answer is 48. Don't even have to go to the calculator for that. If I've only got 48 items to choose from, how many ways can I choose 1 of them? Well, just 48 ways. And that's it. So this is actually why a hand like this is quite valuable. Now, let's compare that to the previous question. 3 red hand cards and 2 black cards. Because there's nothing really specific about this, okay, I mean, it's any 3 red cards, any 2 black cards. That kind of a pattern is quite common, okay? 845,000. There's nothing really special about that. Now, you might have a special scenario. You might have a special hand that has 3 red cards in it, 2 black cards. But what we're trying to get at here is to identify a hand as just 3 red cards, 2 black cards, and not give any more detail than that. That's not a very special hand here. But to say it has 4 jacks, that's very, very specific. There's not many of those, and so it's quite valuable.
They are made up of 3 10s and 2 4s.
Okay, so here we go. They are made up of 3 10s and 2 4s here. Now, compare that to the one just above this here, 3 red cards and 2 black cards. Not being very specific about that. There's a lot to choose from for the red cards, a lot to choose from the black cards. Here, we're being a lot more specific. Instead of saying red, we're being 10s. Well, now remember, each suit has got cards numbered from 2 up to 10, and then the jack, queen, king, ace. In a standard deck of cards, there are only 4 10s to choose from. Okay, there are only 4 4s to choose from. So what we're doing here is we're really limiting the size of the group that we're choosing from. Up here, we were still dealing with the full deck, the full deck really. Half of them are red, half of them are black. That's a lot of cards to choose from. Here, no, we're not. We're really zooming in here. So again, if you're cheating with somebody and you've decided that you're going to send them 3 10s and 2 4s, then what choice do you have to make? Well, I have to decide which of those 4 10s am I going to send. So 4, choose 3. and then for the 4s, 4 choose 2. Okay, and now let's go to the calculator here. So 4 choose 3, 4 choose 2, press enter, and it's just 24 because this is a very, very specific, okay, type of hand here. Now, we could go into a little bit more detail and talk about it, for example, in the context of a poker game, but we don't really have time for that in this particular lesson. But it is an interesting conversation to have with your teacher, or maybe not.
They are all of the same suit.
Okay, to be all of the same suit, okay, we call that a flush. Doesn't really matter what we call it here, but they're all of the same suit here. How many different ways could we do this? Well, we could do this 4 different ways here because the suit could be the heart or the spade or the diamond or the club. And remember, or is always going to be interpreted as addition in this context here. But the number of ways this can happen is going to be the same for all of those, the different suits here, because there's always going to be 13 cards to choose from. So they are all of the same suit. Well, each suit is going to have 13 cards for me to choose from, and I need to choose 5. Now, there are 4 different ways I can do this. It's all going to be exactly the same, so I'm just going to multiply this result here by 4. So let's see how many ways I can do that. 4 times, it'll be 13, choose 5. Okay, so 5,148. Okay, so there are 5,148 ways I can be dealt a group of cards that all have the same symbols on them, if you will. Okay, out of that group of 52 cards where there's 13 of each of those different symbols.
How many lines can be drawn between 5 points that are on a circle?
Okay, now the trick to doing this question here is just to think about how many points do you need to draw a line. The answer is you only need 2. You just need to connect two points here to connect to have a line there. So basically, you've got 5 points on a circle. Okay, you've got this light little circle here. We're just asking how many ways can you connect those points there. And the answer is, well, you've got 5 points to choose from, and all we need are 2, okay, to make a line segment there. So how many ways can we choose 2 out of a group of 5? Okay, well, 5. Over to our probability menu. 5 choose 2. And the answer is 10. Actually, I probably could have counted that out here. We got 1, 2, 3, 4, 5. And then 6, 7, 8, 9. Yeah, 10. 10 different ways I can connect the 5 points on a circle.
How many quadrilaterals can be drawn using the same 5 points?
Okay, now, how many quadrilaterals can be drawn using these same 5 points? Okay, well, a quadrilateral has got 4 lines in it, right? But additionally, it's got 4 points. So really what we're trying to do here is we're trying to find how many ways can I connect 4 points out of this group of 5 here. So 5 to choose from, and whoops, and I'm only going to choose 4. Oops. So 5 choose 4. Now you're going to see something kind of interesting here pop up. 5 choose 4. And notice that the answer is 5. So there are 5 different quadrilaterals that we can create from those 5 points. Interesting to note here that 5 choose 4, if you think about it, is the same as or is equal to 5 choose 1. Okay? So, and the way to think about this is like this here. There are 5 different ways, what I'm looking for here, I should say it like this. Of the 5 points, to create a quadrilateral, I'm trying to grab a group of 4. Now, order is not important, okay? I'm going to connect them in the quadrilateral. I just need to choose which 4 points here. In fact, I don't want to make order an issue at all, because then you start making little zigzags and blah. We don't want that. We just want to pick the 4 points. Now, think about it like this. Every time you do that, Okay, if there's 5 points to choose from and you're choosing 4 of them, you're always leaving a point out. So from a group of 5 points, choosing 4 is the same as, of those 5 points, choosing 1 to be left out. The result is identical. Okay, I'm either choosing these 4 here and ignoring this one, or I'm choosing to ignore this one and leaving the 4 points that I'm going to connect here. This pattern here is going to be the same whenever the 2 secondary numbers add up to the initial number. Those 2 combinations will be the same. It's a wonderful little pattern there, and something that we're going to use later on in this chapter.
How many diagonals can be formed from the vertices of a hexagon?
Okay, now to get this question, you sort of have to know something about the vocabulary here. We're going to talk about the diagonals here, okay? The word diagonal is frequently misunderstood here. This is not a diagonal, okay? It's not, okay? It's an oblique line, and that's typically, we use the word diagonal in place of the word oblique, which is, it is what it is, okay? A lot of times we say things that, yeah, technically don't mean exactly what we're saying here, but everybody gets the gist behind it. This becomes a diagonal when that line connects 2 points in a polygon. Now it's a diagonal. So let's think about this. You've got this hexagon right here, so I'm going to quickly draw one out. We're going to start connecting the dots here. Now, I've just connected the points all along the outside here. These are considered sides. Okay, these are sides of the hexagon. These are not diagonals. Okay, again, this is not a diagonal because it's not connecting 2 points within the shape here. This is a diagonal because it's connecting 2 points and that in a quadrilateral, and the line goes through the quadrilateral. This line segment right here is not going through the hexagon, it's forming the hexagon. This, however, is a diagonal. That's a diagonal. That's a diagonal. Diagonal, diagonal, diagonal. What do we got here? Diagonal, diagonal, diagonal. Did I get them all? Whatever. Anyway, but you get the sense here. So these ones on the outside here are not diagonals. It's the line segments that pass within. Now, how are we going to go about doing this? Well, how many ways can I connect those? How many line segments did I draw? Well, of the 6 points here, I chose 2 to connect. This is going to give me all of the different line segments that I've drawn there. I'm going to subtract from that, though, the ones that are considered the sides. Now, how many sides are there to a hexagon? 6. And so this is going to give me the number of diagonals. Now let's go to our calculator. So 6, choose 2, minus 6. 6 choose 2 is all the different ways that I can connect those dots in a hexagon, the vertices in a hexagon. And I'm subtracting that group of 6 of them that don't count as diagonals, they count as the sides. And the answer is there's 9. Okay, there are 9 different diagonals that I can draw within a hexagon.
How many handshakes will occur between 8 people in a room?
Okay, how many ways can 8 people, or how many handshakes occur if you've got 8 people in the room here? Well, how many people do you need for a handshake? Well, you only need 2. Is order important? No, it's just a pairing. Okay, so that means we just need to select 2 people. So this is going to be 8, choose 2. So that's pretty straightforward there. So 8, over to probability menu, 8 choose 2. So there's 28 handshakes will happen in a group with 8 people, in a room with 8 people.
How many games will need to be scheduled between 10 teams in a league if each team plays each other team once?
Okay, so in this case here we've got 10 teams, and we're just going to have each team play every other team just once, okay? So how many teams do you need for a game? Well, typically just 2, right? I mean, there's not many games I can think of where you'd have more than 2 teams out there. So in the vast majority of the cases here, it's just going to be 2. So of the 10 teams, we just need to find how many ways I can group together 2 of them. So we go to our calculator. Remember, order is not important in this case here. This is just a pairing. We're just grouping two of them together, selecting groups of two. So 10, choose 2. Whoops, and the answer is 45. So if all we wanted to do was have these teams play each other once, we would have to schedule 45 games.
How many games are there if the 10 teams play each other twice?
Okay, now this next question is an important one here. We don't want you getting thrown off by this. So we've stipulated here that each team is going to play every other team twice. Okay, now what's happening here is basically think of it like this. Compare this to the previous question here. We're pairing up the teams. Okay, we know that there was 45 games played when we did that. Then what we do is once that's done, we do it again. And at the end of that, every team will have played every other team twice. So all we're doing is doubling that result. Okay, but it's a bit of an order of operations issue here. This is why we throw the question in. I'm kind of hesitating here because I hope people get this. It's not that you're making this 20 choose 2 or 10 choose 4 or something like this. You're not doubling those pieces there. It's not like the number of teams has gotten bigger or the number of teams you need for the games has gotten bigger. It's the number of games played overall. And remember, 10 choose 2 is the number of ways overall that we can set one team against another. Throw a 2 in front of that, and then we're just doubling the result. 90 games would suffice to have every team play every other team twice.
How many ways can 15 volunteers help at a school carnival if 4 are needed for the ticket booth, 3 at the concession stand, and 8 for the games area? All the volunteers are qualified to work at any of the stations.
Okay, now this is the exception to the rule that I was hinting at before here. We've got 15 volunteers, and we're going to need 4 for the ticket booth, 3 at the concession, and 8 for the games. Now, notice if you add up 4, 3, and 8, you get 15. In other words, everybody here is getting chosen. Okay, everybody here is getting chosen. Now, the reason why that's significant is because that causes this to be something called a partition. What we're essentially doing here is we've got this group of people here and we're chopping this thing up into, in this case, 3 different groups. Okay, ticket booth, concession, and then games here. Everybody gets chosen. So I can do it like this. I've got 15, and here's one way of doing it. I can choose 3 people to go to the ticket booth. And once I've chosen that, I still need to choose a group of people to help out at the concession. Now, once I've chosen the 3 from the 15, I am left with 12 people. I got to choose, I needed 4 for the ticket booth. My mistake, 4 for the ticket booth. It doesn't really matter. And then that leaves me with 11 for the concession. And again, it doesn't really matter. And I'll show you why in just a second here. I'm going to choose 3 people for that. And once that's done, I've got 8 people left over, and I need to choose all 8 of them to go to the game section here. Now, based on what I have told you before, you might look at this and say, well, wait a minute. That looks like I'm choosing from 15 plus 11 is 26. It looks like I'm choosing from 34 people. And I'm choosing, what have I got here? I'm choosing 15 again. But from 34 people. And yeah, I know where people would get thrown off by that. But the real issue here is because everybody is getting chosen. Everybody's getting split up into their different groups here. This 8 choose 8 actually is just going to be the number 1. It works in this particular case. This is the exception to that rule here. This actually is not incorrect. Now, this works, though, as long as everybody gets chosen. If you're not choosing everybody out of this group, you can't answer the question like this. Okay, if not all of these volunteers are getting picked for something, if other people are getting kind of sent away to do something else here, they're just not being chosen, then this kind of an approach doesn't work. But you could do this another way. You could also do this as 15 choose 3 to go to the concession, and then once you've chosen that, you could do 12 choose, let's say, 8 to go to the games, and then you're left with 4 choose 4 to have to go to the ticket booth. That will also work. Those will be identical answers here. Or you could do, for example, we could do 15, choose 8. And once you've chosen that, let's say we choose from the 7 remaining, you choose 4 to go to the ticket booth, and then you've got 3 left over, and you choose the 3 of them to go to the concession stand. It doesn't matter how you go about doing this. Because everybody gets chosen, it'll always be the same result. And let's figure out what that result is. Whoops. Okay, so we'll do 15. We'll do it the way we started here. 15 choose 4 times, what did we do here? 11 choose 3 times 8. I don't really have to do this last one here, but just so you see the whole thing, choose 8. Press enter, and we get 225,225. Okay, and now I tell you what, just to illustrate that you do get the same result regardless of what you do here, let's do this last one here that I did. Let's try 15, whoops, choose 8 times 7, choose 4 times 3, choose 3. And notice again, it's the exact same value. It doesn't really matter what you do. The identifying feature here is note everyone gets chosen. That's what makes this work. If not everybody's getting chosen, then this isn't an appropriate way to work this question through.
How many 5-lettered arrangements can be formed using 3 vowels from the word equation and 2 consonants from the word factor?
Okay, now this is an interesting question, and this is a bit of a thinker here. Is order important? Okay, when you're talking about arrangements of letters. Well, yeah. If you're building a word, the order that the letters come in, that's significant. You change the order of the letters, you change the word. So yeah, order is important here. So this really looks like a permutation. So we're looking for 3 vowels from equation. Well, equation has 1, 2, 3, 4, 5. So you might think, okay, let's do 5 pick 3, or 5 permute 3. And then we need 2 consonants from the word factor. Well, let's got 1, 2, 3, 4. So 4 permute 2. And so there we go. Order is important, so I use permutations. I needed 3 from a group of 5, and then 2 from a group of 4. There you go. But that's wrong. Okay, this is incorrect. And the reason it's incorrect, this is significant here, and it's something you want to be looking out for. When you write it like this, 5p3 multiplied by 4p2, what you're suggesting here is that the vowels always come first and the consonants always come last. There's no mixing. But that's not really the spirit of this problem. The spirit of this problem is that no, you're mixing the letters up. You're looking for the 5-letter arrangements. I'm arranging all 5 letters. Here you're not. You're arranging 3 of them, and you're arranging 2 of them. So how do I go about mixing them? Well, this is what you do, and this is a key question here. It's an important one. It's one that gets we go back to it. Okay, it's a kind of a go-to question. Notice the defining feature here. The key feature of this question is that I am choosing from 2 different groups, and then I want to mix up my choices here. So what I'm going to do here, actually, is I'm going to take the 5 vowels from equation. I'm going to choose 3 of them. Now remember, order isn't important here. If I use a combination, I am suggesting to you that order is not important. Order is important in this problem, but not yet. That's the difference. That's the approach here. Order isn't quite important yet. So I'm going to do 5 choose 3, and then I'll do 4 choose 2. Again, order is not important. Order is not important when I'm getting the letters. Now that I have the letters, now that I've made the choice, how many ways can I permute those 5 letters? And the answer is, 5 factorial. Okay, so this question here is part combination, part permutation, but you got to do the combination first. You got to get your objects here before you can permute them. And again, you would recognize a problem like this because you would be choosing objects from two or more different groups and then mixing them all up. Now, let's just enter this in the calculator. So we got here 5, choose 3, 4, choose 2, and then we're going to multiply that by 5 factorial. And there we go. There are 7,200 different quote-unquote words that we could create using that restriction.
Solve the following algebraically. N choose 2 is equal to 66.
All right, as we've seen in previous lessons here, the trick to this sort of a question right here is to convert this into factorial notation and then to get rid of the factorials. Okay, to solve this algebraically, I need to kind of get this into a form that I can manipulate a little bit easier here. So nc2 is the same as n factorial over n minus 2 factorial 2 factorial. Okay, and that's going to equal 66 here. Now, first thing I'm going to do here is get rid of this 2 factorial down there. Now, 2 factorial is just 2. So I'm going to multiply both sides of this equation by 2, or 2 factorial, doesn't really matter. That's going to get me n factorial over n minus 2 factorial, and that's equals to 132, okay, on the right-hand side. Okay, so I just dealt with that just to get it out of the way. Now I've got n factorial divided by n minus 2 factorial. Well, which is larger? N factorial. So I'm going to expand this out. So the first number here is going to be n. I will multiply it by the next smaller number, which will be n minus 1. I'll multiply it by 2 numbers less, which will be n minus 2. And I'm going to stop right there because I can see my denominator coming out in that. I put the factorial to indicate that I'm going all the way to the end here. And in the denominator I've got n minus 2 factorial. So those two are going to cancel with each other. Okay, n minus 2 factorial over n minus 2 factorial is just 1. And I'm left with n times n minus 1 is equal to 132. Okay, so now what we want to do here is, this is a quadratic, so we're going to expand that out. So we'll get n squared minus n minus 132 is equal to 0. Okay, now we got to factor that. Okay, so let's think here. What are my factors of 132 that differ by 1? Oh, and the answer is minus 12 and then plus 11. So n minus 12 and plus 11. So my answers here is going to be that n is either equal to 12, whoops, or negative 11. But, just as in previous questions here, we don't want the negatives. Okay, the negative makes no sense here. You really can't put a negative in here. Negative 11, choose 2. Doesn't work. 12, choose 2 does though. So the answer here is exactly 12. Now, we could have done that earlier. We could have stopped right here and done that, because remember what this is saying is 2 consecutive integers have a product of 132. Now, you're answering the same question right here. Basically what I'm saying here is 2 numbers side by side have a product of 132. When I factored this, I asked myself the same question. What 2 numbers have a product of 132 and differ by 1? Well, it's the exact same thing. I could have said up here, well, it's got to be 11 and 12. And since n minus 1 is the smaller number here, 12 is n is the larger, n was 12. Anyway, could have answered it right there.
N choose n minus 2 is equal to 28.
Okay. Once again, the initial step here that I got to deal with here is getting rid of the combination notation, converting it to the factorial notation, and then getting rid of the factorials to solve this. So, n choose n minus 2. Now notice I've got variable on both sides here. Got to be careful. So this will be n factorial over, this is going to be n minus n minus 2 factorial. Now I hope that makes sense here. Now I'm not quite done. I'm not quite done. I got to finish this with the n minus 2 factorial. This is going to equal 28. But let's go through and talk about this again. It's the notation here is NCR is equal to n factorial over n minus r factorial r factorial. Think of this as left side choose right side is left side factorial over left side minus right side factorial. So left side factorial, okay, n factorial, yeah, over left side minus right side factorial, right side factorial. Sometimes it's the fact that there's a binomial in there, and there's a little bit of algebra going on inside the not the function notation, the combination notation here that can be a little confusing. So this will be n factorial. Now notice if you distribute the negative through here, the n's will cancel, and you're left with a 2 factorial. N minus 2 factorial equals 28. Oh, there's something you should be vaguely familiar about this. So what I'm going to do is multiply by the 2 factorial, which is just 2, and I get n factorial over n minus 2 factorial is equal to 56. Okay, now we've just dealt with this. N factorial over n minus 2 factorial, I already know is going to become n times n minus 1. And you know what? You're going to see this show up a lot when you're dealing with combination equations. You won't typically see like an n choose 3. And it's not because you couldn't do it. You could do it. But if you have an n choose 3 here, then this becomes a cubic. Okay? And you can solve a cubic, but it's a fair bit more difficult. Okay? N choose 4, it would lead you with a quartic. Again, you could do it, but it would be much more difficult. The expectation here with n choose 2 is you're just going to get a quadratic, and a quadratic should be relatively easy to solve. I will multiply that through, bring the 56 over, then I say, what two numbers who have a product of 56 and differ by 1? Well, that's going to be n minus 8, n plus 7. So n is either equal to 8 or negative 7, but again, the negative doesn't make much sense. So n is equal to 8. And again, I could have got that up here because I'm asking myself the same question. N and n minus 1. Those are two integers that differ by 1 and have a product of 56. Well, that's got to be 7 and 8. The smaller number is this n minus 1, so that's got to be 7, which means n has to be 8. Could have done it right there.